Okay, so the periodic table, the father of the periodic table is a gentleman, last name Mendeleev. And now he kind of gets credit for it, but everybody knows that a lot of people were working on the periodic table. But what he did that kind of made him stand out from everybody else is he published a paper showing a table like this. And there were a lot of elements that had not been identified yet. But he could tell, based on how he had lined things up, which is basically following this pattern here as well, he could tell the rows and the columns had different similar properties. And he could look at the different properties like the density, the kind of texture of the metal, the color, the shininess, right? Its reactivity, its what kinds of elements it liked to hang out with, right? From all of these things, he could predict what the unknown elements' properties would be. And so he did that in this paper, and he was right on so many different things that people were just amazed at how wonderful it was. So it was clear that the periodic table helped answer a lot of questions. And so a lot of effort before and since has been put into trying to organize our elements. So this is why the periodic table becomes valuable to us. So we got columns and rows, periods or groups. And you can see, also known as families, the columns have similar properties. In fact, our last column here on the far right, I'm sure most of you know the name of that family. What's that family? The noble gases, right? Noble gases. And you can think of it as the noble family, like, you know, the royal family. Everybody wants to be like the royal family. And all the elements want to have similar configurations to those of the royal family. All right? So the periodic table is broken into these blocks, as indicated here in this figure. Now, there are certain trends that we introduce to students who are learning chemistry initially that follow very nice patterns. And the elements that follow those patterns the best are called representative elements. And that's these two columns and these last 6 columns there. All right? So those are our representative elements. And then we have our transition elements and our inner transition elements. Okay? The first column here, let's see, the first column, because the reactivity here is so very similar and very reactive, they get this name called alkali metals. Now, alkali is the opposite of acidic. And we haven't talked about this, but you might already know what acidic is, and therefore you could learn something from that, and it might help you remember. Essentially, these elements, like sodium, potassium, rubidium, you put them into water and they'll just explode, right? Have you guys seen that before in videos or something like that? And when you're done, the solution, the liquid that's left over, or the water, the mixture that's left over, is very basic. So not acidic, but basic. And alkali is another name for basic. Okay? So alkaline earth metals, similar types of properties towards water, well, slightly similar. They don't explode, but they will react readily. And then we have our noble gases over here. The 7th column over here, again counting 1, 2, 3, 4, 5, 6, 7, 8, right? Our 7th column is also a pretty popular family called the halogens. Halogens. Every column has a name, but really the alkali metals, the halogens, and the noble gases are probably most often referred to as by their family name. Okay? Now, the periodic table really, I mean, if we're trying to line it up perfectly, would look like this, right? With our inner transition metals here and our transition metals here. However, because of our 8.5 by 11 sheet of paper, right, this is how generally periodic tables are presented. We've talked about the staircase that separates the what? Metals and the nonmetals. What are there more of? Metals. More metals. Okay? Okay? Along that staircase there, we have metalloids or semi-metals, another name that you call that region, except for aluminum. And hopefully that's one that's easy enough to remember because we do have a little bit of experience with aluminum cans, and we know that that's a metal, hopefully. Okay? And then hydrogen, we also talked about being the exception over there. It's a non-metal. All right, so with that information, see if you can talk to your partners and figure out which one of these is correct. Did you find it? Which one is it? Fluorine is a halogen. Very good. Carbon is not a semi-metal. It's actually a what? A non-metal. Sodium is an alkali metal. Very good. And copper is not a representative, or sorry, yes, copper is not a representative element. It's a transition metal. Okay, now some properties of metals. Metals are shiny. You guys probably know that. A pure metal, now when we talk about metals, sometimes we think there's a metal right there. You know, that's metallic. The chair legs here are metallic, right? But those aren't pure metals. Pure metals are pretty easily manipulated, pretty malleable, they call it, right? This is a piece of sodium that's being pulled apart by a chisel. You can see it kind of looks like brie cheese. It has a white coating on the outside, and it's shiny in the middle. That white coating is the sodium that's interacted strongly with the oxygen and the water in the atmosphere. All right, so this person is getting a chunk of sodium to drop into a bathtub somewhere. This is a desiccator. Has some material in here to keep the water, absorbs all the water, so that keeps that dry and keeps it from reacting. So here's a video of them putting that sodium in a piece of water, or in a little bucket of water. Okay, so it's dark, so you can see the little explosion there. You can also do the same thing then.
And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Whoops. With elements that are lower, right? Lower in the periodic table, because as you go down, you get more reactive, right? So.
Well, imagine, if you will, letting off a hand grenade in a bathtub.
So we're at rubidium now. We skipped potassium, but here they're going to put rubidium into a bathtub of water.
Okay, Tickle. Drop the rubidium in the water. Stand back, everybody. This one's going to be bad. 2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Particularly nasty to go off at any time. And that's it. Oh yes. Yeah, I like it already. Now what's that going to do when it hits the water? Imagine a depth charge in a bathtub. Fair enough, mate. I'll leave it to that. Thank you. Okay, John, go for it. Warning, warning, warning. Extreme danger. Clear the area. As cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does.
Okay, so what we saw there is we saw somebody putting some sodium in water, and then some rubidium, and then some cesium, right? Showing that elements in a family have very similar reactivity. Okay, and specifically the alkali metals are explosive when they come in contact with water. So, nonmetals. Nonmetals are not conductive. Was that a question? No.
Yeah.
Okay.
How come lime blows up in water too?
Lime?
What's lime made of?
Calcium. So you got some calcium in there. Yeah, so calcium, does it blow up in water? I haven't had a lot of experience with lime.
Put a lot in.
If you put a lot in, it gets hot and begins to fizzle a little bit? Or just boom?
Oh, I guess if you put like a bottle of water.
A what?
Like in a bottle.
Okay. Yeah, so that's a little bit of a different scenario, right? But if you put lime in water, then it will produce carbon dioxide. And if you seal it, then that carbon dioxide will build up pressure and then try to eventually explode it. Yeah. Okay. So, nonmetals. Metals are conductive, but nonmetals are not conductive. And this means electrons can pass through them. All right, so electricity, right? And let's look at a little bit about how we kind of would do a conductivity test. All right? We have a light bulb, let's say. Okay? And what light bulbs do is they pass electricity through a thin wire here. And as they pass through that wire, the wire begins to light up, to glow. If you were to do that without this bulb around it, the wire would just burn away. It would react with the oxygen, right? But this bulb removes any oxygen so that you just can take advantage of the light. So one wire comes off here, off the edge of your light bulb. The other wire would touch right there. If these two wires need to touch some sort of power source, right? Just because they're touching the light bulb, it doesn't make it go off. Electricity passing, electrons moving through the wire make it light up. And same with a toaster, right? Toasters, you get it's a red light, not very bright. If you cut this off here, anywhere in this wire, then you won't get any electricity flowing through, right? But this would be a good way to test the conductivity of a material. You place a material across there, and if it's conductive, the light would light up, right? So that's what we're talking about when we say conductivity. It doesn't produce electrons, it allows electrons to pass through it. Metalloids are interesting materials, and they've really been what have driven our world for, century or two, right? Because since the advent of the ability to store information on semi-metals, that's where we get computers and all the different devices over the years. And the reason why these initiated the process of being able to store data was because semi-metals or metalloids can act like metals when a voltage is applied. In other words, they can become conductive, but when there's no voltage applied, they will not be conductive. And so that is how you would measure a 1 or a 0, right, in a computer. If there was conductivity, it would be considered a 1 or a 0. I don't know if maybe the computer scientists know the difference between which one is which. But that's also why our data storage is binary. There's only either zeros or ones, right? Two options, which has been a significant limitation. I mean, we haven't really been terribly concerned about it because we've been improving the materials that we've stored data on, and so we can get smaller and smaller devices and more storage. However, we're going to run out of space at some point, and people are trying to work on computers that won't just have the options of 1 and 0, but have the options of 1 through any number, 1 through a million or whatever. Then that would expand storage drastically, right? But how they're going to do that, they still are working on. So, Ionic compounds. We initially talked about ionic compounds being one of the two classes of compounds, with the other class being what? You guys remember? Molecular. So we had ionic and molecular. And we said that ionic compounds we would always be able to identify because they what? They contained a metal, all right? And that's still going to be something that we're going to be able to use. Now, ionic compounds, the strong definition is a compound made of ions, right? But that's not a very good descriptor. I mean, how are you going to know necessarily by looking at it that it contains ions? Well, we're going to get better at it. And one of the ways that we're going to get better at it is by learning what an ion is. Again, an ionic compound, a compound that contains ions. Well, what's an ion? An ion is an atom or a cluster of atoms that has one fewer, or not just one, but has more electrons than it does protons, or fewer electrons than it does protons. So let's look at this atom. Anybody remember this symbol? What is this here? Copper. How many protons does it have? Did everybody get a periodic table now? What was it? 29. 29 protons. Excellent. Could you hand this back to the gentleman in the corner there? 29 protons. If I go like this, copper 60, what is that telling me? All right, 60 is the total of protons and neutrons. Again, this is called our mass number, top left corner. All right. Now, if I told you that this copper had a positive charge on it, what that means is it's no longer a neutral atom. So it doesn't have the same number of protons as it does electrons. Okay? Now, if it's neutral, it has 29 electrons because the periodic table says that it should have 29 protons. So if it's neutral, it has 29 electrons. With a positive charge, sometimes, and when you're in a hurry and you're doing lots of different parts of a problem, and then you come along something like this, it's a positive charge. It doesn't mean there's one more electron. It's not like adding an electron, right? It just means that there's one more proton than there is electrons, right? Could we have added a proton to the copper to make it a positive charge? Can't work that way, because if you add a proton to copper, what would it do to it? It would make it zinc, right? Adding a proton to copper would make it zinc. A long time ago, alchemists were trying to convert lead to gold, right? That was a good source of a lot of chemical discovery, because kings were interested in doing this, and they said, hey, can you convert lead to gold? And they did a lot of work trying to do that. But it was not something that was in their realm of possibility. It's not even really in our realm of possibility still. And we understand very well why not now, right? You would need to do what to lead to convert it to gold? Did you guys find lead on the periodic table? Yeah, you'd have to take away protons. How many? One more periodic table? Yep. 3 protons. You need to take away 3 protons to make every atom of gold. For every atom of gold. Or sorry, for every atom of lead to make it gold. Okay? So, that's not something that chemistry can do. It doesn't mess around with the number of protons. Chemistry messes around with the number of electrons on an atom. And we can remove and add electrons to situations. So if there's a positive charge, that means we just have an imbalance of electrons, and the positive charge was created by removing an electron. So, copper 60 with a positive charge, how many electrons does this species have? Okay, so here we go. Protons, neutrons, and electrons. How many protons does copper have? We said that earlier. 29. How many neutrons does this copper 60 have? 31. And how many electrons does this species have? It doesn't have 29 because apparently, well, if it had 30, it would have more electrons, and so this would be what kind of a charge? Negative. So it must be that it has how many electrons? 28. 28 electrons. Now we can see 28 electrons, 29 protons. Oh yeah, there's one proton that doesn't have an electron, so it has a positive charge. And this atom now is an ion because we've given it a positive charge. All right? So if I drew something like this, N3 minus, how many electrons, how many protons, how many neutrons? Well, we don't have to worry about neutrons. Well, I can do something up here. Let's see. How many protons, neutrons, and electrons does this species have? N3 minus. How many protons? 7. Good. Neutrons? 8. 8 plus 7, that gives us our mass number up there. Electrons? 10. So it has a -3 charge on it. So that's 3 additional electrons. Good. So we have 2 different ions up here on the board. One we formed by doing what with electrons? Removing an electron, right? For this one. And this one we made an ion by doing what? Adding 3 electrons. All right? So those are ions. Negatively charged ions we call anions, and positively charged ions we call cations. All right? And I have a little joke to help you remember. I don't know if the joke's necessary. You guys probably can already figure out a way to remember it. But here's the joke. So there's this dog and a cat, and they're at a restaurant, and the dog says, "You look sad." And, no, sorry. Cat says, "I'm sick." And the dog says, "Are you sure?" And the cat says, "I'm positive." Get it? Because he's a cat what? Cation, right? Cations are positive. All right? Pretty good joke, huh? So, cations are positive. Anions are the other one, negative. Too bad they're not called dog ions, but cations are positive. Okay, good. So, when I am given 2 ions like this, here's an iron plus 3 ion. How would I form an iron plus 3 ion from an iron atom? How would that happen? In terms of electrons, what had to happen? Lose 3 electrons, that's right. And to form an oxygen ion, adding 2 electrons. Now, can I predict how iron with a plus 3 charge and oxygen with a -2 charge. Now see how I wrote -2 instead of 2 minus? Don't get hung up on that. It doesn't matter terribly. It's not a big deal. In the future we'll talk about the difference between those, but it's no big deal. How would these come together then? How would these come together to form a stable compound? Because when you mix iron with oxygen, these ions begin to form to find stability. Okay? So, if you have iron mixing with oxygen, what happens is they come together to form iron oxide, and now I'll put an X and a Y down there. They form iron oxide, and the iron here could be a +3 charge, and the oxygen will be a -2. So how many oxygens are necessary to combine with iron that have a +3 charge? If you go like this, whoops, try that again. So if I have iron X, oxygen Y, this number comes down here, and that number comes down here, and that almost always gives us the right ratio, which makes sense. Because if I have 2 iron +3s, right, and 3 oxygen -2s, those 2 irons lost a total of 6 electrons. And where did they lose them to? It went to these oxygens, right? And those 3 oxygens gained a total of 6 electrons, right? Okay, very good. So then, let's see where we're at now. Okay, so here's a chemical reaction where we take sodium metal, you saw sodium metal, and this time instead of combining it with oxygen gas, we're going to combine it with chlorine gas. So we take
A small piece of sodium metal is placed in a flask and
I'll do the talking. A small piece of sodium metal is placed in a flask containing chlorine gas. Okay, and so then we have some sand down here so that it won't break the flask when it gets really hot. But now there's a piece of sodium, there's the green chlorine in there, and we're going to get a little tiny bit of water, because we know that you put water on the chlorine, or on the sodium, it'll kind of flare up a little bit. And this time, when the flare-up begins, it will make it react with the chlorine gas. And left behind, you have this haze, right? Which is what? What do you think? It's salt. That's right. Sodium chloride. Sodium chloride, which is what you guys have been taught is salt. Have we had any conversations about sodium chloride already, or table salt? Yes. We did? So we told you that there's a couple other things in table salt besides just salt, right? In fact, moving forward from this date on for the rest of your life, the term salt no longer just means table salt. Salt means an ionic compound, all right? So any ionic compound is considered a salt, all right? Very good. But this is what one of the main components in what we call table salt is. So, what's driving this? Why did sodium want to lose an electron and chlorine gain an electron? All right. They want to be not neutral, but they... Okay. So here you have sodium. It's neutral, right? How many protons and how many electrons does sodium have here? 11. But it prefers to be like this if it can be, sodium with a positive charge. And the reason is, like the noble gases, helium has 2 protons and 2 electrons, neon, 10 protons and 10 electrons, argon, 18 protons and electrons, and so forth, down the list there, right? Those happen to be magic numbers in nature. If you have that number of electrons and protons, then your energy is significantly stable. And that's why those elements won't do a lot of chemistry with other elements, because they're stable. So when sodium has 11 protons and 11 electrons, right? It finds itself at the restaurant always wishing that it could be like the noble gases, right? So we have sodium. Wait, I'm going to give him a bigger head. Here's his eyes, right? He's sad, though, right? There's sad sodium, right? And sits down at the bar by chlorine, who's also sad, right? I'm going to make her a girl. Okay? So, they're both sad. Why are they sad? Yeah, because they're not noble gases. Everybody likes neon. Everybody thinks he's so cool. He has 10 electrons, 10 protons. I'm very similar. They should like me too. I just have 11 electrons. That's the only, I have 11 protons too. But I just have one extra electron if I could just get rid of it. And chlorine has a sad story too. What's her sad story? Everybody likes argon. She thinks she's so cool. She has 18 electrons. I have 17. I'm just as cool if I just had one more electron, right? And so they get this beautiful idea that sodium will give up an electron to chlorine, and then both of them will have the number of electrons of a noble gas, right? And so they find some stability in each other's arms, right? Okay, so that's how chemical reactions work, especially amongst the representative elements, right? If you look at iron really quick, 26 electrons, 26 protons, Iron, one of the ways that it likes to do chemistry is by losing 3 electrons. How is that going to help it obtain a noble gas electron configuration? If it loses 3 electrons, who's it like? Iron. If iron loses 3 electrons, who's it mimicking, or who's it like? Vanadium? Is there anything special about vanadium? No, not really. So the transition metals and the intertransition metals don't follow this pattern really well, but the representative elements do follow this pattern. And usually that's about all you learn about in high school chemistry because it's just a nice pattern, right? And you hear things like the octet rule, meaning 8 electrons in the outer shell or whatever, right? So, and we'll, use it as much as we can. But it only really works well with our representative elements. Do you guys remember which ones are the representative elements? The first 2 columns and the what? Last 6. Okay, very good. So, here's our little setup that we have drawn over here, providing power to this light bulb, but we've put a break in the circuit, right? If we put that sort of break in the circuit into just solid sodium chloride, we will not get electricity flowing through this light bulb. If we melt the sodium chloride, we will. And if we use pure water, we won't. But if we put salt in our water, we will. So there's 2 examples. Either the salt dissolved in the water, it forms ions that allow conductivity, or melting the sodium chloride, melting your salt, that will allow conductivity as well. So ionic compounds don't provide a conductive path by themselves unless they're in a liquid state or if they're aqueous, right? All right, so here's our same chart, but now our elements have charges. Do you guys want to try to figure out how many neutrons, protons, and electrons there would be, and also figure out what sign and charge goes there? Think you can do that? Use your neighbor. They might know. Anybody confused about what we're doing? Raise your hand if you think you need some help. You getting this okay? Do you have your slides, or do you need more slides, or? Do you want another one, or no? Okay. All right. The protons is easy, correct? Just on the periodic table. How about cobalt? Is it going to have more electrons than protons or less? Yes, it's going to have fewer electrons than protons, right? How about the bromine species? More electrons than protons or fewer? More electrons, right? And again, the neutrons, how do we find the neutrons? Yeah.
So you take the original proton and multiply by the mass, or do you use a new?
Protons don't change, right? Protons don't change. And electrons are never never in the mass. So the mass number is just protons and neutrons. And because it's including neutrons, it's always going to be more. So you can take that top left number and subtract the number of protons, and that'll give you the neutrons. The mass is only made up of the sum of the protons and the neutrons. Okay, so let's look at the first one. How many neutrons in that species?
33.
All right, 33 protons, 27, and electrons, 24. All right, anybody want to go over that one? The second one's probably just as easy. Okay, maybe 20 seconds to get the last one there if you haven't got it yet. Okay, good. Now remember, the mass number is going to go to the top left for this element. What element is it, you think? Copper. The mass number, top left, mass is the protons plus the neutrons, so it's just going to be the sum of those two. 29 and 27. What kind of charge are we going to have? Positive. Positive 2, because there's more positive charges than negative charges. And that's what that charge means. It doesn't mean you've added or subtracted electrons. It's just the difference between the sum of the electrons. Okay, copper 65 with a +2 charge. All right, anybody want to talk about any of these? Okay, very good. So, using the representative elements, which again are the first 2 columns and the last 6, we can pretty much predict, pretty well, the kind of ion that those elements like to form based on their location relative to the noble gases, right? Just like sodium, we said wanted to form what kind of a charge? A positive 1. It wants to form a positive 1 charge. Because why? Not because chlorine, but because it would like to have the same number of electrons as neon, right? So, potassium, what's potassium's sad story? Have you ever seen potassium at the bar always being sad? Oh, really? Well, sometimes he hangs out at the Seasider. Still sad, drinking some root beer. Why is he sad, though? You ever talk to him? He wants to be like argon, and to do that, he needs to do what? Get rid of an electron. Get a positive 1 charge. He's in the same situation as sodium, right? In terms of both of them wanting to lose an electron. What about rubidium? What's his sad story? Krypton, right? Which would require doing what? Losing an electron and forming a positive 1 charge. So the whole family tells the same story over and over and over. You go to a family reunion, it's ridiculous. They just mope around, right? All the same problems, right? You go to this family reunion, and it's still miserable, but they're all complaining that they just need to do what? Lose 2 electrons, right? Because you look at calcium, 20. Who's the nearest noble gas to be? Argon, 18. So if we could just lose 2 electrons, life would be wonderful, right? So, wanting to lose 1, wanting to lose 2. Or another way of putting it, always going to form a +1 compound, +1 ion when it forms a compound. Always going to form a +2 ion when it forms a compound, right? And what are you going to call the types of compounds that contain these types of elements? Ionic compounds, and these are going to become cations. because they're metals, and any compound that they form will be an ionic compound. Right? Okay, over here, same story as chlorine. Bromine, iodine, and fluorine all want to do what? Gain an electron. So they're all going to want to have a +1 charge in the ions that they, or the compounds that they form. Oxygen, sulfur, and selenium all would like to form what kind of a charge? Wait a second, did I say +1? Did I say -1? Everybody in the halogen family wants to form a -1, and these ones want to form a -2. Nitrogen likes to form a -3. Carbon, what do you think? What does it want to do? If you look at it, it's kind of right in the middle, isn't it? 1, 2, 3, 4, or if it goes the other way, 1, 2, 3, 4, and becomes like helium, right? So it can gain 4 electrons or lose 4 electrons. So you know what we have to do? We have to have a whole nother class on compounds that carbon form, right? And what do we call that class? No. Organic chemistry. Organic chemistry. Organic means chemistry of carbon, all right? So when you go to the store and it says, this is organic salad dressing, then you know that it must have a lot of what in it? No, they've used the name for other things, right? So, but organic chemistry is a whole other class about the kinds of carbon or kinds of compounds carbon can form, because it's essentially infinite, the kinds of things that can do, right? Sodium and chlorine, they're always coming together the same way. Calcium and oxygen, always the